Okay, so our first foray into how we deal with things mathematically in a statistical way, from a statistical mechanics standpoint, linking quantum to observables like temperature, volume, number of particles. The way that we do that is we start to talk about a two-level system. Now, it is an idealized system, okay? So most systems don't have two levels and only two levels, but there are some very important applications to systems and motions where only two levels are ever like practically available. Okay, so if we think about temperatures near room temp, what we like to say is that for vibrations, most molecules are in their vibrational ground state. For electronic transitions, like nearly all, even more so than vibrations, and we kind of see that because of this energy gap, but we'll make those connections in a bit. Nearly all molecules, unperturbed, just at room temperature, are in their electronic ground state. Okay? So thermally, okay, we can kind of see this play out as, oh, it really only looks like there's it really only looks like there's two systems, two different energy levels that we ever really have to consider at all. And then that kind of encapsulates the whole behavior of that situation. Okay. So there are some applications to real world situations. And just to drive some points home that we talked about last time, remember these sort of distributions that we looked at last semester, these Maxwell-Boltzmann distributions, where we're looking at the probability of finding particles with certain energies and how that relates to temperature. This purple graph is the low temperature graph that we drew last semester. And then this red graph is like a higher temperature graph that we drew last semester. These same ideas happen here. Remember that temperature affects these distributions in terms of motion. And so it's going to have a similar effect here in terms of which one of these states are available. We'll actually see that with the two-level system. As you go to higher temperatures, okay, you get more possibility, you get more probability to be able to go to higher energies, okay? But for the most part, at low and high temperatures, you're populating energies that are on the low end of things. And so when we look at a two-level system, or even if we just kind of consider, let's just take vibrations for instance here, all right? At low temperatures, we expect the probability, right, for finding a system with a certain energy, we expect the probability to find this low energy state as being really, really high. Maybe there's one that creeps up here, okay? And remember, these X's aren't representing electrons or anything like that. These X's are saying, okay, this is like a total vibrational energy here, and this is a total vibrational energy here for our system. What's the likelihood of seeing, right, this energy state manifest instead of this energy state? If I increase temperature, what's going to happen, and we'll see this mathematically, is some of these will creep up to the top, okay? Right, so that's the thing that we're going to try to look at from a number standpoint now. So let's look at a two-level system. It is idealized. We know there's more than two vibrational states. We know there's more than two electronic states. But, okay, those two states might be the most important. And so we're going to look at the actual mathematics associated with a two-level system and then know that we have application to those important properties that we look at. So here's what we're going to do. We're going to make this energy level diagram. We're going to call this E0 and we're going to call this E1. So there's our two levels, and these are our two energies. And just for the heck of it, we're going to set E0 equal to 0 kilojoules, 0 joules. We're just going to set it equal to 0, okay? And we can do that without loss of information because really this gap is what matters spectroscopically anyway, okay? So we're going to call this 0 and we're going to call that E1, okay? So now, with this information and with only this information, we're able to calculate, all right, P0. We're able to calculate P1, and we'll be able to calculate an average energy, which remember for us is an internal energy, right? This is all we really need to be able to do that, okay? And we'll be able to look at temperature effects. What does temperature do to all our results here as we increase it, and what does temperature do to these effects as we decrease it. And like I said, so we're really getting the first bit of statistical insight from this nice simple model system. Okay, so let's start with calculating Q. And I mentioned it before, the partition function has all the needed information inside it. It's really the critical factor for doing calculations. The formula we gave you for the partition function was this. So we look at all our observed energies, right, all the possible energies that we have. We sum over e to the minus beta. Remember, beta is 1 over kT. E to the minus beta, all those observed energies. Well, here there's only 2 possible. So if I translate this now to our 2-level system, Q looks like e to the minus beta E0 plus e to the minus beta E1. That's what that sum means. You look at all your possible levels. Well, for 2-level systems, there are only 2, so there's only 2 parts of that sum. So hopefully this is already starting to click now in terms of what this Q looks like. All right. Well, we actually have a value for E0. We arbitrarily set it to 0. E to the 0 is 1. So our Q for this case looks like e to the minus beta E1. All right. Great. This is our Q for our 2-level system. And then the numerical value of E1 determines what Q is in terms of a number. All right. Q has physical meaning. We're going to be able to see that. All right. So it's definitely labeled the partition function, but the physical meaning of Q that we'll be able to see play out here with this example, and then this will be the physical meaning that translates to all of our complicated examples, is Q measures the number of thermally available states. The number of thermally available states is Q. That's hard to see right now, but we'll take a look at it in a bit, right? Let's talk about probabilities first, okay? So, with our Q now established, we can calculate P0, P1, and then actually we're going to jump to the temperature effects because that's where it becomes interesting kind of right away. So here's my population to be in the ground state. This is the probability or the population to be in that E0 state, right? It looks like e to the minus beta E0 divided by Q. And that's our sort of definition from our last video. So it looks like e to the minus beta times 0 over 1 plus e to the minus beta E1. Okay? So P0, we can simplify further. That numerator looks like 1 plus e to the minus beta E1. Okay, this is our population to be in our 0 state. This is the probability to find a system, right, with an energy of 0. P1 similarly, right, looks like, okay, e to the minus beta E1 over 1 plus e to the minus beta E1. And we really can't simplify any more than that, okay? So these are 2 formulas for our 2-level system, okay, that describe the populations. One thing I want to point out off to the side to start, before we get to our temperature analysis, is it kind of makes sense. What's P0 plus P1, right? If you look at this, hopefully you can see mathematically, they have a common denominator, so you'll be able to add them together. You get 1 plus e to the minus beta E1 divided by 1 plus e to the minus beta E1. P0 plus P1 equals 1. And that's important to realize, and it's a nice little check, because if you sum up all your different probabilities, what should you get? You should get 1, because probabilities are normalized, okay? So this is something that we've seen before, and it's a nice little review. But again, here's a population, here's a population. What if I want to do a quick little check? Add these guys together. Do I get 1? Yes. then I'm pretty confident that these are going to be the populations that I can analyze. And remember, population and probability, they mean the same thing. Okay, so let's do a couple limits here. Right. So let's do a high T limit first. Ooh, no, let's do low T limit first. Sorry about that. All right. Okay, so we have to think about where temperature is. And temperature is inside beta. Beta is 1 over kT. So if I make temperature small, what happens to beta? Well, temperature is in the denominator here. So as this gets smaller, beta gets bigger. Okay? So then, where's beta inside, all right, these expressions? Beta shows up in one spot. E to the minus beta, E1. Well, what happens when I have a negative exponential and my beta gets bigger? This decay then occurs rapidly, right? This is then going to be a big value up here, right? A big value, and it's a decay. There's a negative sign. So as you approach lower and lower temperatures, these guys, these e to the minus betas, they start to approach 0. So in this low temperature limit, with this analysis enacted, right, what does P0 start to look like? P0 starts to look like 1 over 1 plus 0. P0 starts to look like 1. What does P1 start to look like? It looks like 0 over 1 plus 0. It starts to look like 0. Now, why does this make sense as a result? Remember, this is all about temperature making states available and the amount of thermal energy, right, that results in a distribution of systems to different states. Here's E0. Here's E1. What happens when I take the thermal energy out? I get to a point where only that bottom state is populated. I get to that situation in this low temperature limit where every time I look and try to find, all right, a system in a certain energy state, there's not enough thermal energy to get any movement up into that higher energy state. It's like all of the population, all of the particles, all of the systems, however you want to look at it, everything's in the ground state. Everything. There's not enough temperature to make a jump. There's 100% probability to be in that bottom state and 0% probability to be in that upper state. And like I said, this makes sense because you suck thermal energy out of a system. What happens? Things go into their bottom state. Things get to that ground energy level. Okay, in general. We know statistics plays a role, like Fermi-Dirac statistic versus Bose-Einstein. Things we mentioned before that we don't have time to get into now. Those will affect how this distribution looks, but just for the sake of argument, just realize that as you suck energy out of the system, everything goes down to its ground state. Okay, so now let's look at the other limit, because that's an important result, and that's true. That's an actual truth, okay, that we can apply to any of our systems that we're going to look at this semester, the non-complicated ones. As you suck energy out, everything kind of creeps down into the low state, the low energy state. Let's do a high T limit now. All right, a high T limit. Well, for a high T limit, remember where T is? It's inside beta. Okay? So inside beta, we have temperature that's now getting big. As temperature gets big, beta now starts to get really, really small, right? Beta is almost approaching 0, depending on what this high T means for us, okay? So where is beta inside our expressions? It's in this term e to the minus beta E1. Well, as beta gets smaller and smaller and smaller, and this starts to approach 0, e to the minus beta E1 starts to approach 1. Because anything raised to the 0 power looks like 1. Now we see another incredibly important result. In the high T limit, P0 approaches 1 over 1 plus 1. It approaches 1/2. What does P1 approach? It approaches 1 over 1 plus 1. It also approaches 1/2. And this is an incredibly important result. The best you can do with temperature is an even distribution. What does a P0 of 1/2 and a P1 of 1/2 really mean to us? It means there's a 50-50 shot to see particles or systems in an ensemble. There's a 50-50 shot to observe an E0 versus an E1. Right? So what this looks like, and this is the best you can do with temperature, is now everything's not in the bottom state. There's an equal distribution between the ground state and the excited state. What this proves, and what I'll state, so it doesn't prove it exactly mathematically, but what it supports and what I'll state as fact is you can never have a population inversion based only on temperature. The best you can do, the high temperature limit, is an even distribution. And this will apply even to our more complicated systems, right? You can't ever have like 5 little x's here and 4 here. That's what I mean by population inversion. You can't have more in excited state than there are in a ground state, just by temperature alone. The best you can do is they have an even distribution or an equal likelihood to be in either state. Okay? A really incredibly important result. Okay. So just for the heck of it, let's take a look. All right. Let's just do, let's stick with the high T limit. And we could do this with the low T limit, but you're going to get the idea. Let's calculate average energy that's equal to U. Okay. So average energy is going to be a sum P sub I E sub I. Okay. So in this limit, and we're just going to do it for a high T limit, okay? So let's write the general example for any temperature, okay? So P1 we knew was 1 over 1 plus e to the minus beta, E1, all right? E0 would be the first part of that sum. The second part would be, okay, P1, which is e to the minus beta, E1 over 1 plus e to the minus beta, E1 times E1, okay? So hopefully now you can see how this translates to a general expression. But now let's apply our high T limit. Okay, let's apply the high T limit to this. And again, try to think about the low T limit yourself and what it would look like and how it makes sense. Well, E0 is 0, so no matter what, this term is 0. But in the high T limit, remember this looks like 1/2. So what you get out for average energy is 1/2 E1 in the high T limit. Right, in the high T limit. Right. Okay, well, how does that make sense? Well, you have a distribution of energies here. There's an equal amount in E0 and E1. This equals 0. So these guys are here. Half of them are here giving you a 0 contribution to the total energy, and half of them are here giving an E1 contribution to the total energy. And what do you see for the total internal energy? 1/2 E1. Okay, so actually it kind of just makes sense what we get out using now this average energy formula, using the populations and the individual energies inside it, right? You should be able to kind of guess what the low T limit of energy is. Based off of defining E0 as being 0, our low T limit is 0. But again, try to do it yourself. Try to make sure that you can come up with that yourself and understand why that is the case. Okay. Let's apply other numbers to this, and let's kind of talk about away from limits for a second. We can start to ask ourselves some interesting questions, okay? So let's say that we have like a really big gap here. Let's just try to see what manifests in terms of actually using the mathematics. Let's say that we have a temperature that's around room temperature, like 300 Kelvin, but let's say we have a gap that's a kilojoule. All right, 10 to the third joules, a kilojoule. Let's say we have a kilojoule gap. What do we expect to see for this 2-level system in terms of populations? Okay. Well, remember, the main thing inside our population is e to the minus beta E1. So let's say if we have that gap as 10 to the third, a gap of a kilojoule. That means that if this is 0, then E1 is equal 10 to the third kilojoules. Okay? This is the main thing that affects our population formulas, okay? So we can actually calculate this out, right? So e to the minus, beta is 1 over kT, E1 over kT, right? E1 is 10 to the third joules, 10 to the third joules. K, you'll see in the front, is in the front of your book, right? It's 1.3807 times 10 to the minus 23rd. Yeah, 10 to the minus 23rd joules, all right, per Kelvin. And temperature is also here as well. So we see mathematically, as soon as we get a temperature or an actual numerical value for energy, we can throw it into this formula, remembering that beta is 1 over kT, right? We do this work in the denominator first. We take whatever that result is, we divide it into 10 to the third. We remember this negative sign is out front, all right? So what we get is e to the minus 2.414 times 10 to the 23rd. If you plug this into your calculator says that's 0, right? Okay, now let's make sense of this result. Because if I go now and I look at P0, right, if I go look in P0, this is 0. So we have 1 over 1 plus, oh, wait a second, it looks like we have our low T result. Right? Well, wait a second, I'm at room temperature, and I'm talking about a low T result. When we go and we look at P1, what are we going to get? We're going to get 0. So, low temperature is always relative to the gap. And that's the point I'm trying to make here, okay? So this is an instance where this E1 is just so much bigger than the E0. Then at room temperature, right, at room temperature, all your particles in your system, all your systems in an ensemble, okay, all of the things that you're trying to analyze from a statistical mechanics standpoint are going to be in the ground state. There's not enough thermal energy to bridge that gap, right? So it actually kind of makes sense in terms of our result. Let's ask ourselves a maybe more interesting question then, right? And then let's link it back to vibrations. Okay. So let's do a two-level system, right? And let's say, okay, we have E0 equal to 0. But let's say we don't know what E1 is. And what we're going to ask ourselves is, what E1 could cause a 75% probability to be in the ground state? Right. What E1 could cause a 75% probability to be in the ground state? Well, 75% probability to be in the ground state, that translates into a P0 as 0.75. Okay. Which equals 3/4, right? Either way you want to look at it. Now we know that this is equal to 1 over 1 plus e to the minus beta E1. So what we'll also need to specify here is a temperature, right? We'll need to specify a temperature, okay? So let's specify a temperature of 300 Kelvin again, because then we'll be able to know beta and we'll be able to analyze this, okay? So let's go through that process. So what we're going to do here is we're going to solve this equation for E1. And this is an algebraic equation you should be able to solve, okay? Now what I get for E1 when I do this at 300 Kelvin, and again, make sure you check my work, but there's only one unknown here because you know what K is, you know what your Boltzmann constant is, and you know what your temperature is now. When I do this, what I get for E1 is I get 4.550562 times 10 to the minus 21. And I didn't pay attention to significant figures, but the units here would be joules. Right? So in this situation, you only have 25% of a probability to be in the excited state. You still have a 75% probability to be in the ground state. This is the gap. Now, just to compare this to something you're kind of used to seeing, E1 in terms of wave numbers, right? is 229 centimeters minus 1. This ends up in the microwave range, right? We're still not quite into that IR range, right? So if you look on like an IR diagram, some things, most of the stuff happens in the thousands of wave numbers, right? So it kind of leads credence to what we said before, right? This small energy gap gives you 25% probability to be in the excited state. Vibrational energy gaps are even bigger than this. So what you get is a more unequal distribution. You get more of a P0 and less of a P1, all right? Which again makes complete sense because what do we say at around 300 Kelvin, at around room temperature? Our P0 for vibrational states is going to be close to 1. So the fact that this shows up in the microwave region, or it shows up in regions less energetic than our IR region, it makes complete sense, okay? All right, so just make sure you know how to do this sort of problem. With two-level systems are definitely things I'm going to ask about on your quiz because they're real simple to kind of get functional forms that we can then analyze in terms of, hey, let's throw a temperature at you, let's throw an energy at you, let's have you calculate an energy. They're just really easy to manipulate relative to the other things that we do, and you still get some important physical results that you can analyze, okay? It's all about how the energy gap compares to the temperature in terms of making these populations manifest.